Right now, more than 13 billion miles from where you're sitting, a spacecraft the size of a small car is hurtling through absolute darkness at 34,000 miles per hour. It has no destination. It has no fuel to steer. It has almost no power left to speak. Within a few years, its last instrument will fall silent, and it will become the loneliest object humanity has ever created. But here is the part that should unsettle you. Voyager 2 will not stop. It will keep moving. Not for centuries, not for millennia. For a span of time so vast that the stars themselves will burn out, go dark, and crumble to nothing while this dead machine continues drifting through a universe that no longer remembers what built it. If this is the kind of deep science storytelling you want more of, hit like and subscribe. Also, before we begin, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, are you comfortable? Let's begin. In the summer of 1977, a spacecraft about the size of a subcompact car sat in a clean room at the Jet Propulsion Laboratory in Pasadena, California. Engineers had been working on it for years. It weighed roughly 722 kilograms, and nearly every gram of that mass had a purpose. Cameras, spectrometers, magnetometers, particle detectors, a radio transmitter, a high-gain antenna shaped like a satellite dish, and 3 small canisters of plutonium-238 that would slowly convert radioactive heat into electricity. There were no solar panels. Where this spacecraft was going, the sun would be too far away to matter. The machine was called Voyager 2. Its mission was to fly past Jupiter, Saturn, and if everything went perfectly, Uranus and Neptune. The entire plan was supposed to last 12 years. After that, the spacecraft would coast outward with no further objectives, no further targets, and no further reason for anyone to keep paying attention to it. Voyager 2 launched on August 20th, 1977, from Cape Canaveral Launch Complex 41, riding a Titan IIIe rocket into the Florida sky. Its twin, Voyager 1, launched 16 days later on a faster, shorter trajectory aimed at Jupiter and Saturn only. The 2 spacecraft were identical in design, but their path through the solar system would diverge almost immediately, and their fates across deep time would be shaped by decisions made before most people alive today were born. To understand why 1977 mattered so much, you need to understand what the solar system was doing at that moment. The 4 giant outer planets, Jupiter, Saturn, Uranus, and Neptune, were approaching a geometric alignment that occurs roughly once every 176 years. In this configuration, a spacecraft launched from Earth could use the gravity of each planet to bend its trajectory and accelerate toward the next one without burning fuel. The technique is called a gravity assist. It works because the spacecraft borrows a tiny fraction of the planet's orbital momentum as it swings past. The planet does not notice. The spacecraft gains enormous speed. This alignment meant that a single probe could visit all 4 outer worlds in a single extended flight. Engineers called the concept the Grand Tour. It had been studied and debated throughout the early 1970s, and when the funding was finally secured, it came with a compromise. The mission would be approved as a Jupiter-Saturn flyby. The Uranus and Neptune legs would be optional extensions, dependent on whether the spacecraft survived long enough and whether Congress kept writing the checks. Voyager 2 reached Jupiter on July 9th, 1979, passing within roughly 570,000 kilometers of the cloud tops. The encounter was transformative. Its cameras revealed details of Jupiter's atmosphere that ground-based telescopes had never captured. It observed changes in the Great Red Spot, mapped the surfaces of the Galilean moons, and captured further images of Io's volcanic eruptions, which Voyager 1 had discovered just 4 months earlier in the first confirmation of active volcanism anywhere in the solar system beyond Earth. Europa showed a surface of cracked ice that hinted at a liquid ocean beneath. Ganymede and Callisto revealed ancient, cratered terrains. In a matter of weeks, Voyager 2 rewrote the textbooks on an entire planetary system. The gravity assist at Jupiter bent the spacecraft's path toward Saturn. 2 years later, on August the 26th, 1981, Voyager 2 passed within roughly 101,000 kilometers of Saturn. It studied the planet's rings in extraordinary detail, revealing structures so fine and so complex that ring scientists would spend decades working through the data. It observed Saturn's atmosphere, measured wind speeds that exceeded those on Jupiter, and studied several moons, including Enceladus, which showed a surface so young and so smooth that something beneath the ice had to be resurfacing it. That mystery would not be solved for another 2 decades. Here is where the story splits. Voyager 1, which had arrived at Saturn about 9 months earlier, was directed to fly close to Titan, Saturn's largest moon. The trajectory required to get close to Titan sent Voyager 1 upward, out of the plane in which the planets orbit. After Titan, Voyager 1 could not visit any more planets. Its grand tour was over. It headed north, away from everything, at an angle that would carry it into interstellar space, faster than any other object humanity had built. Voyager 2 took a different path. Because Voyager 1 had successfully studied Titan, the team at JPL was free to aim Voyager 2 at Uranus instead. This was the optional extension, the part of the grand tour that was never guaranteed. Saturn's gravity bent the trajectory south and outward. 5 years later, on January 24th, 1986, Voyager 2 arrived at Uranus. No spacecraft had ever visited Uranus. Almost everything humanity knew about the planet came from telescopic observations that were limited and blurry. Voyager 2 changed that in a matter of hours. It revealed that Uranus had a magnetic field tilted nearly 60 degrees from its rotational axis, a configuration so unusual that planetary scientists still struggle to fully explain it. The spacecraft discovered 10 new moons and photographed Miranda, a small moon whose surface looked like it had been shattered and reassembled, with cliffs more than 5 kilometers high, among the tallest in the solar system. Another gravity assist. Another years-long cruise. On August 25th, 1989, Voyager 2 made its final planetary encounter, passing within roughly 4,951 kilometers of Neptune, closer than any other planetary flyby in the entire mission. Neptune's atmosphere, which scientists had expected to be bland and featureless given its distance from the Sun, turned out to be violently active. Voyager 2 discovered the Great Dark Spot, a storm system the size of Earth. It measured wind speeds of over 2,000 kilometers per hour, the fastest recorded in the solar system. And when it flew past Neptune's large moon Triton, it found geysers erupting from a surface so cold that nitrogen existed as ice. Triton was geologically alive in a place where temperatures dropped below minus 235 degrees Celsius, cold enough to freeze the air you breathe into solid crystal. Then it was over. After Triton, there was nothing ahead. No more planets, no more moons, no more gravitational targets. The cameras were turned off to save power. Most of the instruments that had been designed for the close planetary encounters were no longer needed. The Grand Tour, the most ambitious robotic exploration mission ever flown, was complete. Voyager 2 had visited 4 planets, dozens of moons, and traveled a path through the outer solar system that no spacecraft had taken before, and none has taken since. And instead of stopping, it kept going. The trajectory that carried Voyager 2 past Neptune did not curve back toward the Sun. It could not. The gravity assist that had made the Grand Tour possible had also given the spacecraft enough velocity to escape the solar system entirely. After Neptune, Voyager 2 was moving at roughly 15.3 kilometers per second relative to the Sun, fast enough that no object in the solar system had the gravitational pull to bring it back. It was heading south, below the plane of the planets, toward the constellations Sagittarius and Pavo. What followed was not a mission in the traditional sense. There were no flyby targets, no approach sequences, no imaging campaigns. What followed was a slow, decades-long crossing of a boundary that most people do not realize exists. The boundary of the Sun's influence. The Sun does not simply shine, it exhales. Every second, it ejects roughly 1 million tons of charged particles outward in every direction at speeds of roughly 400 kilometers per second. This stream of plasma is called the solar wind, and it inflates a vast bubble around the Sun that extends far beyond the orbit of Pluto. That bubble is called the heliosphere. Everything inside it, every planet, every asteroid, every comet in a stable orbit, exists within the Sun's magnetic and particle environment. The heliosphere is not a hard wall. It is a gradient, a transition zone where the solar wind gradually weakens until it can no longer push back against the pressure of the interstellar medium, the thin gas and dust that fills the space between stars. The outer edge of the heliosphere is called the heliopause. Crossing it means leaving the Sun's protective cocoon and entering a region where the particles around you are no longer from your star. They are from other stars, from ancient supernovae, from the general reservoir of material that drifts through the galaxy. Voyager 1 crossed the heliopause in August of 2012. The moment was confirmed by a sharp change in plasma density detected by the spacecraft's instruments. Voyager 2 followed 6 years later, on November 5th, 2018, at a distance of roughly 119.7 astronomical units from the Sun. The crossing was confirmed by multiple instruments, including the Plasma Science Experiment, which measured a steep decline in solar wind particles and a corresponding increase in cosmic rays from outside the heliosphere. Both crossings were historic. Voyager 1 and Voyager 2 are the only human-made objects to have reached interstellar space. The data they returned from the heliopause and beyond is unique. No other instrument, no telescope, no satellite in orbit around Earth can measure what the Voyagers measure from where they are. They are sampling the actual physical environment of the space between stars, and they are doing it with instruments designed in the early 1970s. That last detail matters more than it might seem. Voyager 2 does not carry modern electronics. Its onboard computer processes data at a speed that a modern smartphone would find laughable. Its radio transmitter operates at roughly 20 watts, about the power of a refrigerator light bulb. The signal it sends toward Earth, traveling at the speed of light, takes more than 19 hours to arrive. By the time it reaches the deep space network antennas on the ground, the power of that signal is 20 billion times weaker than the power of a digital watch battery. The fact that we can still hear it at all is a testament to the engineering, both of the spacecraft and of the receiving stations. But the conversation is getting harder every year. Voyager 2's power comes from 3 radioisotope thermoelectric generators, devices that convert heat from decaying plutonium-238 into electricity. At launch, those generators produced enough electricity to power a modest collection of instruments, heaters, computers, and a radio transmitter simultaneously. But the plutonium decays at a fixed rate. Every year, the generators produce a little less. The decline is steady and irreversible, with no way to slow it down, replenish the fuel, or supplement it with any other source. There are no solar panels. The sun, from where Voyager 2 is now, is a bright star and nothing more. As of early 2026, Voyager 2 is approximately 143 astronomical units from Earth. That is roughly 21.4 billion kilometers. It is moving through the constellation Pavo at a speed that will carry it roughly 3.3 astronomical units farther from the Sun every year. Its power levels have dropped to the point where the mission team has been forced to begin shutting down science instruments, one by one, each shutdown a quiet act of triage performed across billions of kilometers of empty space. The timeline of those shutdowns tells its own story. In October of 2024, the plasma science experiment was powered down. Its orientation relative to the flow of interstellar plasma had limited the data it could collect, and the power it consumed was needed elsewhere. In March of 2025, the low-energy charged particle instrument was shut off. The cosmic ray subsystem is scheduled to be turned off in 2026. After those shutdowns, Voyager 2 will have 2 instruments remaining: the magnetometer and the plasma wave subsystem. Engineers at JPL believe that with careful power management, at least 1 instrument can remain operational into the early 2030s. That is not guaranteed. The spacecraft is nearly 50 years old. It has been operating in the vacuum of deep space, exposed to cosmic radiation, micrometeorite impacts, and temperature extremes for longer than most of the engineers currently managing it have been alive. Every component is aging. Every system is degrading. The mission team has described the situation with a phrase that is remarkable for how plainly it states the stakes. Every day could be our last. When that last day comes, when the final instrument draws more power than the generators can provide, and the radio transmitter falls silent, something will change about Voyager 2 that is difficult to describe in purely technical terms. The spacecraft will not stop moving. Its velocity through interstellar space will be unchanged. Its trajectory, shaped by gravity assists performed decades ago, will continue along precisely the same path. The golden record bolted to its side, a gold-plated copper disc carrying sounds and images of Earth, will still be there. The cameras, though long since turned off, will still be mounted in their housings. The antenna, though no longer transmitting, will still point in the general direction of a sun it can no longer see. The direction Voyager 2 is heading right now was not chosen for what comes after the mission. It was chosen for a moment that lasted less than a day. When mission planners designed the Neptune encounter in the early 1980s, they faced a decision that would permanently determine the spacecraft's outbound trajectory. The primary scientific objective at Neptune, beyond imaging the planet and its rings, was to fly through the radio shadow of Triton, Neptune's largest moon. By passing behind Triton as seen from Earth, the spacecraft's radio signal would pass through Triton's atmosphere on the way to the Deep Space Network antennas. The way that atmosphere bent and absorbed the signal would reveal its composition, temperature, and density. It was an elegant technique, one that had been used at other planets earlier in the mission, but it required the spacecraft to approach Neptune from a very specific angle. To achieve the geometry needed for the Triton radio occultation, mission designers sent Voyager 2 skimming over Neptune's northern hemisphere and then diving sharply beneath the ecliptic plane, the flat disk in which the planets orbit. The closest approach to Neptune, less than 5,000 kilometers above the cloud tops, bent the trajectory southward at roughly 48 degrees below the ecliptic. The passage through Triton's radio shadow worked perfectly. The science was extraordinary, and the trajectory was locked. That southward bend is the reason Voyager 2 is heading in the direction it is heading today. Not toward any star, not toward any scientific target. South and outward, 48 degrees below the plane of the planets, a direction determined entirely by the angle needed to pass behind a moon for a few minutes in August of 1989. The decision was made for reasons that expired the same day they were fulfilled. The consequences of that decision will govern the spacecraft's path through the galaxy for the rest of time. There is something disorienting about this when you sit with it. The trajectory that will carry Voyager 2 past Ross 248, past Sirius, through billions of years of galactic orbit, was chosen so that a radio signal could pass through the thin atmosphere of an ice moon for a fraction of an hour. The entire future of the spacecraft, its path through the death of stars and the cooling of the universe, was fixed by a constraint that no longer matters, serving a purpose that was achieved and completed within hours and never needed again. No one at the Jet Propulsion Laboratory in the years when Neptune's encounter geometry was being designed was thinking about where the spacecraft would be in 40,000 years. They were thinking about Triton. They were solving an immediate problem with the tools available, and in doing so, they drew a line through the galaxy that the spacecraft will follow for longer than the galaxy will exist in its current form. But Voyager 2 will no longer be a spacecraft in any meaningful sense. A spacecraft is a machine that communicates with the civilization that built it. It sends data. It receives commands. It participates in a relationship between here and there. When the signal stops, that relationship ends. Voyager 2 becomes something else. It becomes an object. A piece of metal and silicon and plutonium moving through space with no instructions, no audience, and no purpose. Not broken, not crashed, just disconnected. The mission team knows this is coming. They have been preparing for it for years. The instrument shutdowns are part of a plan to delay the silence as long as possible, to squeeze every last watt of usable power into every last bit of irreplaceable data. Suzanne Dodd, the Voyager project manager, has spoken publicly about the emotional weight of these decisions. Shutting down a science instrument on a spacecraft that will never be serviced, never be repaired, never be upgraded, and never be replaced is not just a technical decision. It is an ending. But the engineers also know something else. They know that when the silence comes, Voyager 2's journey does not end. It transforms. The mission ends. The voyage does not. The spacecraft that was built for a 12-year tour of the outer planets will continue moving through interstellar space for a length of time that makes its entire operational lifespan look like a rounding error. the 12 years of the Grand Tour, the 50 years of extended mission, the few remaining years of weakening signal. All of it. Everything Voyager 2 has done while humans could still hear it, will eventually amount to less than the opening fraction of a second in a journey measured in trillions of years. That is not poetry. That is trajectory mechanics. And what happens after the signal stops, what happens when Voyager 2 enters the longest and darkest phase of its existence, is the part of this story that most people have never heard. Because the near future path of Voyager 2 has been mapped in detail. The stars it will pass, the distances involved, the timescales that stretch from thousands of years to millions, all of it has been calculated using real astrometric data from missions like the European Space Agency's Gaia Observatory. And the picture that emerges when you follow that path far enough forward is not romantic. It is not a message in a bottle drifting toward a distant shore. It is something colder, stranger, and more unsettling than any ending the mission's designers ever imagined. Because Voyager 2 is not heading toward a destination. It is heading into a future so deep that the meaning of the word destination begins to collapse under its own weight. What lies ahead, in the first 40,000 years alone, will make the entire history of human civilization look brief. There is a room at the Jet Propulsion Laboratory in Pasadena, California, where a small team of engineers monitors the health of the two most distant machines humanity has ever built. The room is not dramatic. It does not look like a movie set. There are desks, screens, and the quiet hum of computers processing data that has traveled from beyond the edge of the sun's influence to reach them. The people who work here are among the last in the world who can still speak to Voyager 2. And they know that within a few years, possibly sooner, the conversation will end permanently. The spacecraft does not know this. It cannot know this. Voyager 2 has no awareness of its own condition. It has no model of its own future. It responds to commands and transmits data according to routines coded into its memory decades ago, and it will continue doing so until the electricity stops flowing. But the engineers know, and the way they talk about the spacecraft reveals something about the relationship between a civilization and the objects it sends into the dark. They do not talk about Voyager 2 the way you talk about a piece of equipment. They talk about it the way you talk about something you are losing. The power situation is arithmetic. It cannot be negotiated with. Each of the 3 radioisotope thermoelectric generators aboard Voyager 2 contains a core of plutonium-238. The plutonium decays at a fixed rate governed by its half-life, roughly 87.7 years. As it decays, it produces less heat. Less heat means less electricity. At launch in 1977, the 3 generators together produced approximately 470 watts. By 2026, that output has fallen to somewhere around 220 watts, less than half of what the generators produced at launch, and the decline is irreversible. Every system on the spacecraft requires a share of those remaining watts. The radio transmitter needs power to send signals home. The onboard computer needs power to process commands and format data. The attitude control thrusters need power to keep the antenna pointed toward Earth. The heaters that protect sensitive electronics from the deep cold of interstellar space need power to keep running. And the science instruments, the entire reason the spacecraft still matters to anyone, each draw their own share. For years, the mission team has been cutting. Heaters were turned off first, exposing components to temperatures they were never designed to endure, and hoping the engineering margins built into the hardware in the 1970s would hold. They held. Backup systems were powered down, redundant circuits were deactivated, every non-essential draw on the power budget was eliminated, and when there was nothing non-essential left, the team began cutting into the essential. By 2026, the ongoing shutdown sequence will have reduced Voyager 2 to its final two instruments. The magnetometer, which measures the strength and direction of magnetic fields in interstellar space, and the plasma wave subsystem, which detects oscillations in the plasma surrounding the spacecraft. These are the last two windows through which the spacecraft can observe anything. The magnetometer maps the invisible architecture of the interstellar medium, detecting how the Milky Way's magnetic field drapes and folds through the space between stars. The plasma wave subsystem listens for pressure waves moving through the thin ionized gas that fills the void, converting them into audible frequencies that sound when played through a speaker on Earth, like the faint crackle of static from an impossibly distant radio station. Both instruments are measuring phenomena that no other device in human history has been positioned to detect. When they go dark, the measurements stop permanently. No future telescope or satellite can replicate them, because no other instrument is where Voyager 2 is. Engineers believe that with continued power management, at least one of these instruments can remain active into the early 2030s. But that estimate carries uncertainty that the numbers alone do not capture. Voyager 2 has been operating in deep space for nearly 5 decades. Its components were manufactured in an era when the integrated circuit was still young. The wiring, the connectors, the mechanical joints that keep the antenna pointed, all of it is aging in an environment where temperatures hover near minus 270 degrees and cosmic rays strike the electronics with energies no laboratory on Earth can replicate. The team at the Jet Propulsion Laboratory has described the daily reality of managing the spacecraft with an honesty that borders on grief. Every day could be our last. When the final instrument goes silent, the deep space network antennas, the massive dish receivers in California, Spain, and Australia that have been listening to Voyager 2 for nearly half a century will hear nothing. The frequency that carried data from Neptune, from the heliopause, from interstellar space itself, will go quiet. There will be no dramatic sign-off, no final image, no closing message, just a signal that weakens below the threshold of detection and then is gone. To understand what will be lost in that moment, you need to understand what it actually takes to hear Voyager 2 right now. Because the act of listening to this spacecraft is itself one of the most extraordinary feats of engineering that most people have never heard of. The Deep Space Network is a system of 3 antenna complexes, positioned roughly 120 degrees apart around the Earth. One is located near Goldstone in the Mojave Desert of California. One is near Canberra, Australia, at a facility called Tidbinbilla. And one is near Madrid, Spain. The spacing is deliberate. At any given moment, no matter how the Earth is oriented in its rotation, at least one of the 3 complexes has a line of sight to any spacecraft in deep space. There is always someone listening. Each complex operates multiple antennas of different sizes, but the workhorses for Voyager communication are the 70-meter dishes. These are among the largest steerable radio antennas ever built. The dish near Canberra, designated Deep Space Station 43, is the only antenna in the southern hemisphere capable of communicating with Voyager 2, because the spacecraft's trajectory carried it south of the ecliptic plane after the Neptune encounter. If that single antenna goes down for maintenance, there is no backup. Voyager 2 goes unheard until the dish comes back online. In March of 2020, an extended upgrade to the camber antenna left Voyager 2 unable to receive commands from Earth for nearly 11 months. The spacecraft continued operating on autopilot during that period, following pre-programmed routines, alone in a way that was not symbolic, but literal. The signal that reaches these antennas from Voyager 2 is almost incomprehensibly faint. The transmitter pushes its signal across more than 21 billion kilometers of expanding wavefront. By the time that signal arrives at Earth, the power reaching the antenna is measured in fractions of a femtowatt. A femtowatt is 1/4,000,000th of a watt. The signal is so weak that the thermal noise generated by the motion of atoms in the antenna's own receiver electronics is louder than the signal itself. To extract Voyager 2's data from this noise, engineers use cryogenically cooled amplifiers that operate near absolute zero. Even then, the process requires hours of integration time, mathematical filtering, and error correction algorithms designed specifically for this purpose. The data rate has been reduced multiple times over the decades. At Jupiter, the nearest of its planetary encounters, Voyager 2 transmitted data at rates up to 115.2 kilobits per second. By Neptune, the farthest flyby, the rate had dropped to roughly 21.6 kilobits per second as the growing distance weakened the signal. Today, the rate has fallen to roughly 160 bits per second. A single image from the Neptune flyby would now take days to transmit. The spacecraft is still speaking, but it is whispering, and the whisper is growing fainter every year as the distance increases and the transmitter power declines. The engineers who operate the Deep Space Network have described the experience of tracking Voyager 2 in terms that reveal how personal the relationship has become. These are people who spend hours locked onto a signal from a machine that was built before many of them were born, crossing their fingers that the link holds, that the aging hardware survives another day, that the next command sequence arrives intact after its 19-hour journey. When the signal finally drops below the detection threshold for the last time, it will not be an abstraction for them. It will be the end of a conversation they have been maintaining for the length of a human career. And after that final whisper fades, the 70-meter dishes will continue to turn. They will track other spacecraft, receive other signals, serve other missions, but nothing they point at will ever be as far away as Voyager 2. And nothing they listen to will ever carry the same weight of silence when it stops. That moment will mark the end of the Voyager 2 mission. It will not mark the end of Voyager 2. The spacecraft will continue moving through space at approximately 15.3 kilometers per second relative to the Sun, which translates to roughly 34,320 miles per hour. That velocity was set by the gravity assist at Jupiter, Saturn, Uranus, and Neptune. No engine is maintaining it. No fuel is being burned. Voyager 2 is coasting on momentum borrowed from 4 giant planets decades ago. And in the frictionless vacuum of interstellar space, there is almost nothing to slow it down. Almost nothing, but not exactly nothing. The interstellar medium, the thin gas that fills the space between stars, exerts a faint drag on any object moving through it. The density of this gas is extraordinarily low, roughly 1 atom per cubic centimeter in the region Voyager 2 currently occupies, but over timescales of millions and billions of years, even that faint resistance accumulates. The effect is negligible on human timescales, but it is real, and over the deep future it will slightly reduce the spacecraft's velocity. Gravitational encounters with passing stars, rogue planets, and dense molecular clouds will also perturb the trajectory in ways that become increasingly unpredictable as the timeline extends. But for the first several tens of thousands of years, the path is calculable, and what lies along that path has been mapped with remarkable precision, thanks to a mission that has nothing to do with Voyager. In 2013, the European Space Agency launched a spacecraft called Gaia into an orbit around the Sun at a point roughly 1.5 million kilometers from Earth. Gaia's job is to measure the positions, distances, and motions of stars with an accuracy that previous surveys could not approach. By its second data release in 2018, Gaia had catalogued the 3-dimensional positions and 3-dimensional velocities of more than 7 million stars. That dataset gave researchers something they had never had before. A detailed moving map of the stellar neighborhood, precise enough to project the future positions of nearby stars across thousands and millions of years. In 2019, Corinne Baylor-Jones at the Max Planck Institute for Astronomy and David Ifanokya at the Jet Propulsion Laboratory used the Gaia data to do exactly that. They integrated the trajectories of 7.4 million stars and the 4 outbound spacecraft, Voyager 1, Voyager 2, Pioneer 10, and Pioneer 11, through a model of the Milky Way's gravitational field, searching for the closest encounters over the next million years. The results are the most precise predictions we have of Voyager 2's near-future path, and they are both fascinating and deeply clarifying about what the word destination actually means when applied to an uncontrolled object moving through a shifting field of stars. Voyager 2's first notable stellar encounter occurs in approximately 40,000 years. The spacecraft will pass within roughly 1.7 light-years of Ross 248, a small red dwarf star in the constellation Andromeda, also known as HH Andromedae. Ross 248 is a dim, cool star with about 14% of the Sun's mass and roughly 19% of its radius. It is a flare star, prone to sudden bursts of brightness caused by magnetic activity on its surface. At the time of Voyager 2's passage, Ross 248 will actually be the closest star to our Sun, briefly overtaking the Alpha Centauri system as its galactic orbit brings it within roughly 3 light-years of our solar system. 1.7 light-years is the closest Voyager 2 will come to this star. To feel what that distance means, consider that 1 light-year is approximately 9.5 trillion kilometers. 1.7 light-years is roughly 16 trillion kilometers. Voyager 2 will not graze this star. It will not enter its system. It will pass through a region of space that, while closer to Ross 248 than to any other star at that moment, is still so far away that the star's gravitational influence on the spacecraft will be essentially zero. Ross 248 will be a faint red point of light in the distance, slightly brighter than it appears from Earth today, but still just a point. This is not a flyby in any sense that the word carries when applied to Voyager 2's encounters with the planets. At Jupiter, the spacecraft passed within 570,000 kilometers. At Neptune, fewer than 5,000. The passage near Ross 248 will occur at a distance roughly 3 billion times greater than the Neptune flyby. Voyager 2 will not study this star. It will not photograph it. Its cameras have been off for decades, and even if they were still running, the star would be too far away to show as more than a dot. The encounter is notable only because, in a galaxy where the average distance between stars is roughly 4 to 5 light years, 1.7 light years counts as close. After Ross 248, the next significant marker comes much later. In approximately 296,000 years, Voyager 2 will pass within roughly 4.3 light years of Sirius, the brightest star in Earth's night sky. Sirius is a binary system, a hot white main sequence star paired with a small, dense white dwarf. At 4.3 light years, the encounter is even more remote than the one with Ross 248. Voyager 2 will drift past the Sirius system at a distance comparable to the current gap between our Sun and Proxima Centauri, close enough to qualify as being in the stellar neighborhood, far too distant for any meaningful physical interaction. National Geographic's coverage of the Voyager trajectory lists additional encounters beyond Sirius, including the stars Delta Pavonis and GJ754, which the spacecraft would approach roughly 100,000 years after the Sirius passage. The Baylor-Jones and Farnokia study identified approximately 60 stars that the 4 outbound spacecraft will approach within a reasonable distance over the next million years. Of those, roughly 10 will be within 2 parsecs, or about 6.5 light years. None will be within a distance where the word encounter carries any physical meaning beyond shared proximity in the emptiness. Here is the point that changes the story. None of these are destinations. Voyager 2 is not heading toward Ross 248. It is not aiming for Sirius. It is not navigating toward any star or system. It is following a path through space that was set by the specific angles and velocities of 4 planetary gravity assists performed between 1979 and 1989. The stars it passes near are not targets. They are coincidences of trajectory and timing, brief moments when the geometry of a moving spacecraft and a moving star happen to bring them into relative proximity before both continue on their separate paths through the galaxy. The distinction is critical because it defines what Voyager 2's future actually looks like. A spacecraft with a destination has an arrival. It has a moment when the journey ends and something new begins. Voyager 2 has no such moment. Every stellar passage is temporary. Every point of closest approach is followed by an increasing distance as the spacecraft and the star diverge. There is no orbit to enter, no system to explore, no surface to land on. Each encounter is a flyby in the emptiest possible sense of the word. 2 objects in the same general region of space for a cosmically brief period before separating forever. It is worth pausing to feel what those intervals actually mean, because numbers like 40,000 years and 296,000 years are easy to say and almost impossible to absorb. 40,000 years ago, modern humans shared the planet with the Neanderthals. The last ice age was approaching its peak. Every city, every nation, every written language, every scientific discovery, every war, every work of art that humanity has ever produced fits inside the window between that moment and this one. Voyager 2 will not reach the vicinity of Ross 248 until an equivalent span of time has passed again. Everything that has happened in human history would need to happen twice over, back to back. before the spacecraft arrives at its first stellar neighbor. And when it arrives, as we have discussed, nothing will happen. It will pass at a distance of 1.7 light years and continue onward into the next gap. The next gap is roughly 256,000 years long. That is more than 40 times the length of all recorded civilization. The entire span from the first written language to the present day would need to repeat more than 40 times over before the spacecraft reaches the vicinity of Sirius. And when it arrives, as we have discussed, nothing will happen. It will pass at a distance of 4.3 light years and continue onward into the next gap. And Sirius, like Ross 248, is not a stop. It is a point of minimum distance. The spacecraft passes, the distance begins to increase again, and the next interval begins. These gaps are not empty in the narrative sense of creating suspense between events. They are empty in the physical sense. During those tens of thousands of years, Voyager 2 will be surrounded by nothing it can detect, nothing it can interact with, and nothing that can interact with it. There will be no landmark to pass, no boundary to cross, no change in the environment perceptible to any instrument the spacecraft carries, if any were still functioning. The interstellar medium is so uniform, so featureless, so devoid of structure on the scale of a spacecraft, that the experience, if experience is even the right word for an unpowered machine, would be one of perfect, unchanging sameness, stretching across millennia. This is the texture of Voyager 2's future. Not a sequence of encounters separated by travel time, but a single continuous emptiness interrupted, at intervals measured in geological ages, by the briefest proximity to a star that does not know the spacecraft exists. And between those encounters, there is nothing. Not nothing in the casual sense, nothing in the literal physical sense. The interstellar medium is the closest thing to a perfect vacuum that exists in nature. Between the stars, the density of matter drops to roughly 1 atom per cubic centimeter. For comparison, the air you are breathing contains approximately 25 quintillion molecules per cubic centimeter. The space Voyager 2 is moving through is emptier than any vacuum chamber ever built on Earth, emptier by a factor so large that the comparison breaks down entirely. In this emptiness, the spacecraft will spend the overwhelming majority of its existence. The stellar passages are so brief relative to the time between them that they barely register. 40,000 years to reach the vicinity of Ross 248, 256,000 years more to reach the vicinity of Sirius, another 100,000 years to the next notable stars. The gaps between these markers are measured in tens of thousands of human lifetimes, and each marker, when it comes, is not an event in any physical sense. It is just the moment when the distance to a particular star happens to reach its minimum value before beginning to grow again. The Oort cloud adds another layer to the early phase of this journey. The Oort cloud is a theoretical shell of icy objects believed to surround the solar system at distances ranging from roughly 2,000 to 100,000 astronomical units from the Sun. It is thought to be the source of long-period comets, objects that take thousands or millions of years to complete a single orbit. No spacecraft has ever directly observed the Oort cloud, and its existence is inferred from the trajectories of comets that appear to originate from that distance. Voyager 2, currently at roughly 143 astronomical units, has not yet entered the Oort cloud's inner boundary. Based on its velocity and trajectory, it will begin passing through the Oort cloud's inner regions within the next few thousand years, and will not exit the outer boundary for approximately 20,000 to 30,000 years. Some estimates extend that passage to 60,000 years or longer, depending on the assumed outer boundary. During this passage, Voyager 2 will be moving through a region of space that is still technically within the Sun's gravitational domain. The Sun's gravity extends far beyond the heliopause, and the Oort cloud represents the outermost reservoir of objects that are gravitationally bound to our star. But the influence of the Sun at these distances is extraordinarily weak. The objects in the Oort cloud orbit so slowly that a single trip around the Sun can take millions of years. For Voyager 2, moving at escape velocity, the Sun's gravity is a fading whisper. It slows the spacecraft slightly, but it cannot turn it around. The departure is permanent. Beyond the Oort cloud, if such a boundary can even be defined precisely, Voyager 2 enters a regime where its relationship to the solar system is purely historical. It came from there. It was built there. Its trajectory was shaped by objects there. But it is no longer part of that system in any gravitational or physical sense. It belongs to the galaxy now, and the galaxy does not care about it. That last sentence is not a poetic flourish. It is a statement about physics. The Milky Way contains somewhere between 200 billion and 400 billion stars, along with vast clouds of gas and dust, dark matter halos, and the gravitational influence of a supermassive black hole at its center. Voyager 2, with a mass of roughly 722 kilograms, is gravitationally insignificant on every scale the galaxy operates at. It will be pushed, pulled, and deflected by forces it has no ability to resist or even detect. Its path through the galaxy will be shaped not by its own design or intention, but by the slow, massive motions of objects millions of times more powerful than it is. The Baylor-Jones and Farnokia study included a line in its conclusion that is easy to read past, but difficult to forget once you absorb what it means. They noted that the timescale for a spacecraft to collide with a star is on the order of 10 to the 20th power years. That is 100 quintillion years. A number so large that writing it in standard notation would require 20 zeros after the 1. The current age of the universe is approximately 13.8 billion years. 10 to the 20th power years is roughly 7 billion times the current age of the universe. What that number means is this: Voyager 2 is not going to hit anything. Not soon. Not in a million years. Not in a billion years. The galaxy is so incomprehensibly empty, and the distances between objects so vast that a tiny spacecraft moving at 15 kilometers per second can travel for a span of time that dwarfs the entire age of the cosmos and still not collide with a star. It will orbit the galactic center, pass through different spiral arms, encounter different stellar neighborhoods, and drift through regions of space that do not yet exist in any catalog. And it will do all of this as an intact object, carrying the golden record, carrying the cameras, carrying the dead instruments, for longer than the stars themselves will last. That is the fact that transforms this story from a tale of exploration into something else entirely. Voyager 2 was designed to survive for 12 years. It has survived for nearly 50. It will fall silent within a decade, and then it will continue to exist as a physical object in the Milky Way for a period of time that makes the entire history of stars look brief. The stars that Voyager 2 will pass near in the next few 100,000 years, Ross 248, Sirius, Delta Pavonis, and the others, are themselves temporary. Ross 248 is a red dwarf. It will burn for trillions of years, far longer than our sun, but even it will eventually exhaust its hydrogen and fade. Sirius, a hot, massive star, will burn through its fuel in a fraction of that time and end its life as a white dwarf within the next billion years or so. The stars along Voyager 2's path are not permanent landmarks. They are passing features in a landscape that is itself dissolving, and Voyager 2 will outlast them. Not because it was built to, not because anyone planned for it, simply because it is small, it is cold, it is moving, and there is nothing in its path large enough and close enough to stop it. The same emptiness that makes its journey so lonely is also what makes it so enduring. In a universe where everything that shines eventually goes dark, the things that survive longest are the things that never shone at all. That realization opens the door to a timescale most people have never been asked to consider. Not thousands of years, not millions, not even billions. The trajectory of Voyager 2 extends into a future measured in tens of trillions of years. A future in which the universe itself will be fundamentally different from the one the spacecraft left behind. The stars will be gone. The galaxies will have merged or dispersed. The cosmic background temperature will have dropped to a fraction of a degree above absolute zero. And somewhere in that darkness, a 722 kilogram object built in Pasadena, California in the 1970s will still be moving. What that future looks like, and what it means for the spacecraft drifting through it, is where this story goes next. Everything discussed so far, the planetary flybys, the heliopause crossing, the stellar passages near Ross 248, and Sirius, all of it fits within a window of roughly 300,000 years. That is the foreseeable future of Voyager 2. The part of its journey that can be plotted with reasonable confidence using current star catalogues and trajectory models. 300,000 years sounds immense. It is nearly 30 times longer than the entirety of recorded human history. But in the context of what comes next, it is a prologue, because Voyager 2 is not leaving the galaxy. It does not have enough velocity to escape the Milky Way's gravitational pull. The solar system orbits the center of the galaxy at roughly 220 kilometers per second. Voyager 2, even with the speed it gained from 4 planetary gravity assists, is moving at less than a tenth of the sun's galactic orbital velocity. That is fast enough to escape the solar system, but far too slow to escape the galaxy. When you combine the spacecraft's motion with the sun's orbit around the galactic center, the result is a trajectory that is slightly different from the sun's, but still firmly bound to the Milky Way. Voyager 2 will orbit the center of the Milky Way. Just as the sun does, just as every star in the solar neighborhood does. The difference is that its orbit will gradually diverge from the sun's, carrying the spacecraft through regions of the galaxy that our star will never visit. The orbital period of the sun around the galactic center is approximately 225 to 250 million years. One complete trip around the galaxy. In the time since the sun formed, roughly 4.6 billion years ago, it has completed somewhere between 18 and 20 orbits. Voyager 2, following a slightly different orbital path, will complete similar circuits on a similar timescale, drifting through the galaxy's spiral arms, passing through regions of dense star formation and regions of relative emptiness, nudged and tugged by every gravitational influence it encounters along the way. To picture what this means, it helps to understand the basic geography of the Milky Way. The galaxy is a barred spiral roughly 100,000 light-years across, with a central bar-shaped structure surrounded by sweeping spiral arms. The Sun sits in a relatively minor arm called the Orion Arm, roughly 26,000 light-years from the galactic center. Inward lies the Sagittarius Arm. Outward lies the Perseus Arm. Further inward still, closer to the dense, radiation-heavy core, lies the Scutum Centaurus Arm, one of the galaxy's two major spiral arms. As the Sun orbits the galactic center, it does not stay in the same arm. The spiral arms are not rigid structures. They are density waves, regions where gas and stars are temporarily compressed, like traffic jams on a highway. Stars pass into and out of these denser regions over millions of years. The Sun has passed through multiple spiral arms during its 4.5 billion year life, spending time in regions of intense star formation where supernova rates are higher and radiation levels are elevated, and time in the quieter inter-arm spaces where the stellar density drops and the neighborhood is calmer. Voyager 2 will do the same, but on its own slightly different orbital path. Over hundreds of millions of years, the spacecraft will cycle through spiral arms and inter-arm voids, passing through regions where the dust density is higher and regions where it is lower, encountering different gravitational environments that subtly alter its trajectory with each passage. No two galactic orbits will be identical. The galaxy itself is changing. New stars are forming, old stars are dying. Gas is being consumed and replenished by supernova explosions. The spiral pattern itself evolves over timescales of hundreds of millions of years. Each time Voyager 2 completes a circuit and returns to roughly the same region of the galaxy, the landscape will have shifted. During passages through spiral arms, the spacecraft will be exposed to higher concentrations of interstellar dust and a greater flux of cosmic rays from nearby supernovae. These are the periods of greatest erosion risk. In the inter-arm spaces, the environment is gentler, and the spacecraft surfaces will weather more slowly. Over billions of years, the cumulative effect of these alternating environments will determine how much of the spacecraft survives, and in what condition. There is a specific hazard worth noting. Giant molecular clouds, vast regions of cold, dense gas where new stars are born, represent the most concentrated structures in the interstellar medium. Some of these clouds contain hundreds of thousands of solar masses of material, compressed into volumes a few hundred light-years across. When Voyager 2's orbit carries it through or near one of these clouds, the drag on the spacecraft increases, the dust impact rate rises, and the gravitational influence of the cloud itself can bend the spacecraft's trajectory in unpredictable ways. The Oberg simulations accounted for these encounters and found that the gravitational deflections from molecular clouds could significantly alter Voyager 2's long-term orbital path, sometimes flinging it into higher or more eccentric orbits, sometimes pulling it closer to the galactic core. This means that Voyager 2's galactic orbit is not a stable, repeating ellipse. It is a chaotic trajectory, sensitive to every gravitational encounter, every passage through a denser region, every interaction with the galaxy's evolving mass distribution. Over billions of years, the spacecraft's orbit will wander, drifting through regions of the galaxy that no current model can predict with certainty. The trajectory is determined not by the spacecraft's design or intention, but by the accumulated gravitational history of every object it has passed near since it left the solar system. In 2024, Harvard astrophysicist Avi Loeb and his undergraduate student Shokruz Kakarov calculated the long-term galactic trajectory of Voyager and the other outbound NASA spacecraft, using a detailed model of the Milky Way's mass distribution. Their results, submitted for peer review, showed that within approximately 1 billion years, Voyager will have travelled to the opposite side of the Milky Way disk relative to the Sun. 1 billion years. The number is so large that the human mind tends to flatten it into an abstraction, but the physical reality it describes is specific and unforgiving. Within 1 billion years, the Sun itself will have changed beyond recognition. Solar luminosity increases over geological time as the core contracts and heats. Within roughly 1 billion years from now, the Sun will be approximately 10% brighter than it is today, enough to trigger a runaway greenhouse effect on Earth. The oceans will evaporate. The atmosphere will be stripped of water vapor by ultraviolet radiation. Earth will become a dry, sterilized world, uninhabitable by any life form we know of. The planet that built Voyager 2, the civilization that designed it, the species that dreamed of the stars and then actually reached them, all of it will be gone long before the spacecraft completes its first full circuit of the galaxy. And the spacecraft will not know. It will drift past stars that have no connection to its origin, through molecular clouds that did not exist when it was launched, in a galaxy that has continued to evolve without any awareness of the tiny metal object threading through its structure. By the time Voyager 2 reaches the far side of the Milky Way, the Sun will still be burning, but Earth will be dead. By the time it completes a few more orbits, the Sun will have exhausted its hydrogen fuel, swollen into a red giant, shed its outer layers into a planetary nebula, and collapsed into a white dwarf, a dense, fading ember roughly the size of Earth, but containing about 60% of the Sun's original mass. The solar system as Voyager 2 knew it will no longer exist. That transformation deserves closer attention, because it is the erasure of everything the spacecraft came from. Roughly 5 billion years from now, the Sun will begin to run out of hydrogen fuel in its core. As the core contracts and heats, the outer layers of the star will expand enormously. The Sun will swell to more than 100 times its current diameter, engulfing the orbits of Mercury and Venus. Whether the expanding Sun will reach Earth's orbit is still debated. Some models suggest Earth will be swallowed. Others suggest the planet will survive at the outer edge of the red giant envelope, baked to a molten shell but still technically intact. In either case, the planet will be unrecognizable. Every trace of the civilization that built Voyager 2, every city, every fossil, every geological record, every artifact left behind, will be destroyed by temperatures exceeding 1,000 degrees. The red giant phase will last roughly 1 billion years. During this time, the Sun will lose mass through powerful stellar winds, shedding its outer layers into a slowly expanding shell of gas. This material will form a planetary nebula, a glowing cloud of ionized gas illuminated by the intense ultraviolet radiation of the exposed core. Viewed from a distance of a few light years, the dying Sun will be briefly spectacular, a luminous bubble of gas with a tiny, brilliant point of light at its center. Then the nebula will fade. The gas will disperse into the interstellar medium, mixing with the raw material from which the future stars will form. The core, now exposed, will be a white dwarf, an object roughly the size of Earth, but with a mass of about 60% of the Sun's original mass. It will be incredibly hot at first, with a surface temperature exceeding 100,000 degrees, but it will have no internal energy source, but it will have no internal energy source, no fusion, no burning, just a dense ball of carbon and oxygen, slowly radiating its stored heat into space over timescales, measured in billions and then trillions of years. The planets that survive the red giant phase, if any do, will continue to orbit the white dwarf, but in a profoundly altered system. Jupiter, the planet whose gravity first bent Voyager 2's trajectory towards Saturn, will still be there, but orbiting a dying ember instead of a living star. Saturn's rings, made of ice, will have long since sublimated. The moons that Voyager 2 photographed will still exist as physical objects, but in a system illuminated by a light so faint that they will be virtually invisible. Voyager 2 will be somewhere else entirely, billions of kilometers away, billions of years into its own separate journey, with no instrument left running that could detect the change, even if it were close enough to observe it. The sun that powered the clean rooms where the spacecraft was assembled, the sun that warmed the faces of the engineers who designed it, the sun whose gravity it borrowed from and then escaped, will have become a cooling cinder no brighter than a candle seen from 1,000 kilometers away. The home is gone, the spacecraft remains, but the galaxy will still be alive, stars will still be forming, supernovae will still be detonating, the spiral arms will still be rotating, the interstellar medium will still be cycling gas and dust into new generations of stars. For the first several billion years of Voyager 2's galactic journey, the universe will look recognizable, different in detail, shifted in configuration, but fundamentally the same kind of cosmos that the spacecraft depart from. Stars burning hydrogen, planets orbiting stars, light filling the space between them. That does not last. In approximately 4 to 5 billion years, the Milky Way will collide with the Andromeda Galaxy. This is not a prediction based on uncertain models. It is one of the most firmly established projections in modern astrophysics, derived from precise measurements of Andromeda's velocity toward us. The two galaxies are approaching each other at roughly 110 kilometers per second, and the collision, once it begins, will reshape both galaxies completely. The word collision is somewhat misleading. Galaxies are mostly empty space. When two galaxies merge, the stars within them almost never hit each other. The distances between individual stars are so vast that even when two galaxies pass through each other, the probability of any two stars colliding is negligibly small. What does happen is gravitational disruption on a massive scale. The tidal forces between the two galaxies will distort their shapes, fling stars into new orbits, trigger waves of star formation as gas clouds are compressed, and eventually reshape the two spiral structures into a single, larger, elliptical galaxy. Astronomers have given the merged galaxy various informal names, but what matters for this story is simpler. The galaxy Voyager 2 was born into will no longer exist in its current form. The spacecraft will survive the merger. Not because it is tough or well built, but because the merger itself poses almost no direct threat to an object as small as Voyager 2. The gravitational reshuffling will alter the spacecraft's orbit around the new galactic center, potentially flinging it into a wider or more eccentric path, but the odds of a direct collision with a star or planet during the merger remain vanishingly small. Voyager 2 will ride out the collision the same way most stars will, by continuing to move through a galaxy that is rearranging itself around it. The merger itself will be one of the most visually spectacular events in the history of the local universe, though it will unfold so slowly that no human lifespan could perceive its motion. The first signs will appear millions of years before the galaxies physically overlap. Andromeda, currently visible from Earth as a faint smudge of light in the northern sky, will grow steadily larger and brighter across the millennia. At some point, it will no longer be a distant object. It will fill the sky, a vast spiral of hundreds of billions of stars stretching from horizon to horizon, its arms and dust lanes visible in naked eye detail. If any observer existed to watch, the sky would contain 2 full galaxies, each one sprawling across the darkness, each one pulling gravitationally on the other. The first passage will not be a head-on collision. The 2 galaxies will swing through each other, their stars passing like 2 swarms of fireflies, crossing paths in an open field. Almost none of the individual stars will collide, because the distances between them are so vast relative to their sizes. But the gravitational interaction between the 2 galactic masses will be enormous. Tidal forces will stretch both galaxies into long, curving tails of displaced stars. The clean spiral structures will warp and distort. Streams of stars will be flung outward into intergalactic space, forming bridges and loops of luminous material that arc across millions of light years. The gas clouds within both galaxies will not pass through each other as cleanly as the stars. When 2 molecular clouds collide, they compress, and compressed gas, in astrophysics, means star formation. The merger will trigger a burst of new star creation across both galaxies, lighting up regions that have been dark for billions of years with the fierce blue light of young, massive stars. For a brief cosmological moment, the merging system will blaze with a luminosity far exceeding either galaxy alone. Some of these new stars will be massive enough to burn through their fuel in just a few million years and explode as supernovae, seeding the merged galaxy with heavy elements and radiation. After the first passage, the 2 galaxies will swing apart, slowed by their mutual gravity, then fall back toward each other for a second passage, and a third. Each pass will bleed away kinetic energy through a process called dynamical friction, where the gravitational pull of stars and dark matter converts orbital energy into random stellar motions. Over roughly 1 to 2 billion years, the repeated passes will slow the galaxies enough that they can no longer separate. The 2 spiral structures will dissolve. The stars from both galaxies will settle into a single, larger, more diffuse structure. An elliptical galaxy. No spiral arms, no defined disk, just a vast, roughly spherical cloud of stars orbiting a common center of mass. This merged galaxy will be the last large structure that Voyager 2 inhabits. It is the final stage on which the drama of the Stelliferous era plays out. Inside it, stars will continue to form for a time, fueled by whatever gas survived the merger. But the rate of formation will slow. The raw material will be consumed, and eventually, one by one, the last generation of stars will ignite, burn, and go out. After that, the structure that remains will be a galaxy in name only. A collection of remnants, a graveyard with no visitors. Jesse Oberg, the researcher who modeled the Voyager spacecraft's deep time trajectory through the galaxy, estimated that during the Andromeda merger, there is roughly a 1 in 5 chance that a given object could be ejected from the merged galaxy entirely, flung into intergalactic space by a gravitational 3-body interaction. If that happens to Voyager 2, the spacecraft would leave the galaxy and enter a void so empty that the already sparse interstellar medium would seem crowded by comparison. The erosive threat from dust would drop dramatically, but the isolation would become absolute. No nearby stars, no galactic structure, just an object moving through intergalactic space for timescales that stretch beyond comprehension. If it remains inside the merged galaxy, Voyager 2's long-term survival depends on a different kind of hazard. The interstellar medium is not truly empty. It contains gas, dust, and cosmic rays, and over millions and billions of years, these take a toll on any physical object moving through them. In 2022, researcher Jesse Oberg presented work at the American Astronomical Society meeting that modeled the long-term physical degradation of the Voyager spacecraft and their golden records across deep time. The study used the Gaia star catalogue to trace the spacecraft's trajectories through the galaxy's dust environment, simulating thousands of possible orbital paths and the cumulative damage each would inflict. The primary threat is micrometeorite erosion. Tiny grains of dust, each one far too small to see with the naked eye, strike the spacecraft at relative velocities that can exceed tens of kilometers per second. Each impact is individually negligible, but over millions of years, the cumulative effect is a slow sanding away of exposed surfaces. Oberg's simulations showed that the rate of erosion depends heavily on the spacecraft's orbital path through the galaxy. Voyager 2's trajectory is more chaotic than Voyager 1's, passing through regions with higher dust concentrations, which means its surfaces will erode faster. The golden record, mounted on the outside of the spacecraft, is partially protected. The engraved playing surface faces inward against the spacecraft body, shielded from direct dust impacts. The outer cover, which carries the instructions for playing the record, is more exposed. Oberg's analysis suggested that the golden record's engraved content could remain at least partially legible for roughly 5 billion years, though the outer surface would be significantly degraded by that point. The erosion would not happen uniformly. Different orbital paths would expose the spacecraft to different dust environments, and the chaotic nature of Voyager 2's future orbit means the degradation timeline carries significant uncertainty. Cosmic rays pose a different kind of threat. High-energy particles from distant supernovae and other energetic events penetrate the spacecraft's structure and gradually damage its materials at the atomic level. Over billions of years, this radiation can weaken metals, degrade polymers, and alter the crystalline structure of solid components. The spacecraft will not shatter or crumble in any sudden way, but it will slowly become more brittle, more porous, more fragile. The Voyager that exists 10 billion years from now will be the same shape as the one that left Earth, but its materials will be subtly and irreversibly changed. Despite all of this, the spacecraft is expected to endure. Oberg's conclusion, presented with appropriate scientific caution, was that depending on their orbital look with dust clouds, the Voyagers may be able to survive for timescales stretching into the trillions of years and potentially far beyond that. The phrasing he used was careful and staggering. Trillions of trillions of trillions of years. That phrasing opens a door into a future that requires an entirely different framework to understand. Because by the time Voyager 2 has existed for even a single trillion years, the universe it inhabits will have changed so fundamentally that the word universe barely applies in the same sense. The current era of cosmic history has a name. Astrophysicists Fred Adams and Gregory Laughlin, in their landmark 1997 paper on the long-term fate of the universe, called it the Stelliferous Era, the era of stars. It began roughly 1 million years after the Big Bang, when the first stars ignited and it will continue for approximately 100 trillion years. During this era, the dominant feature of the universe is exactly what you see when you look at the night sky. Stars, burning hydrogen, producing light, heat, and the raw materials for planets and life. Every galaxy you have ever seen in a photograph, every nebula, every star cluster, every familiar feature of the cosmos exists within the stelliferous era. 100 trillion years from now, it ends. The death of the stelliferous era is not a sudden event. It is a slow fade. The most massive stars, the blue supergiants and hypergiants, have already been dying for billions of years. They burn through their hydrogen fuel in mere millions of years and explode as supernovae, leaving behind neutron stars and black holes. Medium-sized stars like the Sun last longer, roughly 10 billion years, before expanding into red giants and shedding their outer layers. But the most numerous and longest-lived stars in the universe are the red dwarfs. Tiny cool stars with less than half the mass of the Sun. They burn their hydrogen so slowly, so frugally, that their lifetimes stretch into the trillions of years. The smallest red dwarfs, those with roughly 8 to 10% of the Sun's mass, are expected to remain on the main sequence for 10 to 20 trillion years. They will be the last true stars in the universe, the final sources of sustained nuclear light. One by one, as even these patient furnaces exhaust their fuel, they will cool, dim, and fade. The last red dwarf to die will mark the end of an era that began with the first light in the cosmos. After it goes dark, no new stars will form. The raw materials, the cold gas clouds that collapse under gravity to ignite nuclear fusion, will have been consumed or dispersed. The process that has defined the universe for its entire luminous history will simply stop. What remains after the last star dies is what Adams and Laughlin called the degenerate era. It is dominated by the remnants of dead stars, white dwarfs, the cores of medium-mass stars, slowly cooling over trillions of years but producing almost no light. Neutron stars, the ultra-dense cores of more massive stars, spinning down and fading. Brown dwarfs, objects too small to have ever sustained hydrogen fusion in the first place, drifting cold and dark. And black holes, from stellar mass remnants to the supermassive monsters at the centers of galaxies, slowly growing by accreting whatever matter drifts close enough to fall in. The degenerate era is not empty. It is not a void. It is a cosmos populated by objects, but objects that produce almost no light, almost no heat, and almost no energy. The only significant illumination during this era will come from rare, catastrophic events. The collision of two white dwarfs producing a supernova. The merger of two neutron stars releasing a brief flash of radiation. These events will occur perhaps once every trillion years across an entire galaxy. Between them, darkness. To understand what this transition looks like from the inside, imagine compressing the entire remaining future of star formation into a single visual sequence. First, the blue and white stars vanish. These are the most massive and most luminous stars in the universe, and they are already dying now. They burn through their hydrogen in a few million years and explode as supernovae, leaving behind neutron stars and black holes. Within a few billion years of the present, the population of blue supergiants in any given galaxy will have been drastically reduced. The night sky, if anyone were alive to observe it, would grow noticeably dimmer, though still rich with the warm light of medium and small stars. Next, the yellow stars go. Stars like the Sun have lifetimes of roughly 10 billion years. 10 trillion years from now, Every sun-like star that will ever exist will have already been born, lived, and died. Their remains will be white dwarfs, scattered throughout the galaxy in enormous numbers, glowing faintly with residual heat, but producing no new energy. Each one will cool at a rate so slow that it takes longer than the current age of the universe for them to dim by a single perceptible increment. Then the orange stars follow. K-type dwarfs, cooler and smaller than the Sun, last roughly 15 to 30 billion years. They will outlive the Sun by a wide margin, but they too will eventually exhaust their hydrogen and transition to white dwarfs. Their departure from the main sequence will be unremarkable. No supernova, no dramatic nebula, just a slow dimming, a gradual transition from a living star to a cooling remnant. And then only the red dwarfs remain. These are the smallest, coolest, most frugal stars in the universe. An M-type red dwarf with 10% of the Sun's mass burns its hydrogen so slowly that its projected lifetime is measured in trillions of years. Some estimates place the lifespan of the smallest red dwarfs at 10 to 20 trillion years, though no red dwarf anywhere in the universe has yet had time to die of old age. They are all still in their infancy relative to their potential lifespans. When every other category of star has burned out, the red dwarfs will still be shining, dim and cool, the last campfires in a darkening universe, but even they are not permanent. Across the trillions of years, even the most frugal red dwarf will consume its last atom of hydrogen fuel. The final generations of these stars will not end in explosions. They will simply grow cooler, dimmer, and redder until they can no longer sustain fusion. They will transition to a state that has never yet existed in nature. A fully cooled stellar remnant, sometimes called a black dwarf, though the universe is not yet old enough for any white dwarf, let alone a red dwarf remnant, to have reached that state. The first black dwarfs are still trillions of years in the future. When the last red dwarf dies, the stelliferous era ends. The universe goes dark in a way that the word dark cannot adequately capture. Not dark the way a room is dark when you turn off the lights. Dark the way the inside of a stone is dark. No source of sustained luminosity anywhere. No star burning hydrogen anywhere in the observable universe. The only light comes from the slow cooling of remnants and the rare, catastrophic collision between them. 250 trillion years from now, the universe will be deep within this era. The stelliferous era will have been over for more than 150 trillion years. Every star that ever shone will have either exploded, collapsed, or faded into a cooling remnant. The galaxies themselves will have changed. Stars within them will have been gradually ejected through gravitational interactions, a process called dynamical relaxation, in which repeated close encounters between stars slowly redistribute energy, sending some stars inward toward the central black hole and others outward into intergalactic space. Over timescales of 10 to the 19th or 20th power years, most galaxies will have lost the majority of their stellar remnants to ejection, with a smaller fraction spiraling inward and being consumed by the central black hole. This is the universe that Voyager 2 will be moving through 250 trillion years from now. Not a universe of stars and planets and light, a universe of cooling remnants and growing black holes and vast, dark emptiness. The spacecraft will still be there, its velocity slightly reduced by billions of years of faint drag from the interstellar medium, will still carry it through whatever remains of galactic structure. Its surfaces, eroded by dust and radiation, will be worn but recognizable. The golden record, if Oberg's estimates hold, may still carry traces of its engravings, faint impressions in metal that were made by human hands in a workshop in 1977. And this is the critical point, the one the title of this story asks you to confront. 250 trillion years from now is not a destination that Voyager 2 is heading toward. It is not a place. It is not an arrival. It is a time. A point on a timeline so long that the entire age of the current universe, all 13.8 billion years of it, fits inside it more than 18,000 times over. The number is not a calculation of when Voyager 2 will reach something. It is a description of how long the spacecraft will continue to exist after everything it was connected to has ended. The sun will be gone. Earth will be gone. The solar system will have been dismantled by the sun's death and by the slow gravitational erosion of passing stars. The Milky Way will have merged with Andromeda and then lost most of its remaining structure through dynamical evaporation. The stars that Voyager 2 once passed near, Ross 248, Sirius, Delta Pavonis, will all have burned out, each one ending as a cooling remnant no brighter than the spacecraft itself. The constellations visible from Earth, the patterns that ancient humans named after gods and animals, will have dissolved billions of years before this moment, as the stars that form them moved apart on their own galactic orbits. 250 trillion years from now, Voyager 2 will not be near anything. It will not be approaching anything. It will not be arriving. It will be doing what it has been doing since the early 2030s, when its last instrument fell silent and its transmitter went dark. It will be drifting, unpowered, unguided, unaware, and alone, in a universe that no longer contains the kind of light that human eyes were built to see. And even this is not the end. The degenerate era, as Adams and Laughlin defined it, stretches from roughly 10 to the 15th power years to 10 to the 37th power years after the Big Bang. The upper end of that range is one followed by 37 zeros. At that time scale, even the remnants begin to change. If proton decay is real, a process predicted by some grand unified theories of particle physics, but not yet confirmed experimentally, then the protons and neutrons that make up ordinary matter will eventually disintegrate. White dwarfs, neutron stars, and every solid object in the universe, including Voyager 2, would slowly dissolve at the subatomic level, their matter converting into radiation and lightweight particles over timescales of 10 to the 34th to 10 to the 41st power years. Whether proton decay occurs is one of the great open questions in physics. If it does, then Voyager 2's physical existence has an ultimate expiration date, one measured in a number so vast that even the trillions feel small beside it. If proton decay does not occur, then the spacecraft, or whatever eroded, radiation-damaged remnant of it persists, could endure for timescales that approach the truly incomprehensible, drifting through the black hole era and beyond into a darkness so complete that the word universe loses any connection to the concept it was coined to describe. But at 250 trillion years, proton decay has not yet begun. The spacecraft is still intact in a recognizable sense. It is orbiting the remnant of a merged galaxy, or drifting through intergalactic space, surrounded by cooling white dwarfs and ancient neutron stars, and the faint hiss of the cosmic microwave background, itself stretched and cooled to a temperature almost indistinguishable from absolute zero. And it is carrying Bolted to its side, a disc of gold-plated copper etched with the sounds of a world that existed for the briefest flicker of cosmic time and then vanished. It is worth pausing to consider the physical environment surrounding the spacecraft at this timescale. The cosmic microwave background radiation, the remnant glow of the Big Bang that currently fills all of space at a temperature of roughly 2.7 Kelvin, will have cooled to a fraction of a degree above absolute zero. The wavelength of that radiation will have been stretched by the expansion of the universe to the point where individual photons carry almost no energy at all. The ambient temperature of the universe will be so low that the concept of warmth will have no physical referent anywhere outside of decaying remnants. The distances between objects will have grown. The expansion of the universe, which is currently accelerating under the influence of dark energy, will have pushed distant galaxy clusters far beyond the observable horizon. The merged remnant of the Milky Way and Andromeda, if Voyager 2 remains gravitationally bound to it, will be an isolated island of dead stars in an expanding void. Other galaxy groups will have receded beyond the point where their light could ever reach the spacecraft, even given infinite time. The observable universe for any hypothetical observer will have shrunk to a single aging galaxy surrounded by nothing. Within that island, Voyager 2 will continue its orbit. The galactic structure will have changed profoundly. Most stellar remnants will have been ejected through dynamical relaxation. The central supermassive black hole, the merged descendant of Sagittarius A star, and the black hole at the center of Andromeda, will have grown by consuming whatever matter drifted close enough to cross its event horizon. A thin halo of remaining remnants, white dwarfs, neutron stars, brown dwarfs, and black holes of various masses will orbit the central black hole in the sparse skeleton of what was once a galaxy of hundreds of billions of living stars. And somewhere in that halo, or perhaps flung into a wider orbit by some ancient gravitational encounter, the spacecraft will still be there. A few hundred kilograms of metal, silicon, and spent plutonium. Eroded, irradiated, colder than anything on Earth has ever been, but structurally intact. Still carrying the record, still carrying the cameras, still carrying the magnetometer that measured the fields of 4 planets and the plasma between stars. All of it silent, all of it dead, all of it enduring. That disk was designed as a message, a greeting from Earth to whoever might find it. The engineers and scientists who created it imagined a moment of contact, a future intelligence encountering the record, decoding its instructions, and hearing the voices and music of a species from a small, warm planet orbiting a yellow star. That scenario required 2 things: someone to find the record, and a universe in which finding it was possible. 250 trillion years from now, both of those conditions may have expired, and what remains is not a message waiting to be found. It is an object that has outlasted the context that gave it meaning, moving through a cosmos that offers no audience, no light to read by, and no frame of reference to make sense of what it carries. What that means and why it is more unsettling than any distance or any danger is where this story ends. Begin with a simple question. What is a destination? In ordinary language, a destination is the place you are going. It implies intention. It implies arrival. It implies that at the end of the journey, something happens. You reach the place. You stop. You do whatever it was you traveled to do. The journey has a shape because the destination gives it one, a beginning, a middle, and an end. Voyager 2 had destinations. Jupiter was a destination. Saturn was a destination. Uranus and Neptune were destinations. Each one was planned, each one was reached, and each one produced something: data, images, discovery. The word fit because the spacecraft was doing what a spacecraft is supposed to do. It was going somewhere specific, and when it arrived, people were waiting to receive what it found. After Neptune, the destination stopped. The Voyager Interstellar mission was not a mission to reach a place. It was a mission to keep listening for as long as the spacecraft had the power to speak. The heliopause was crossed, yes, and that crossing was a milestone, but it was not a destination in the way Jupiter was. No one planned to stop there. No one planned to do anything there except measure the environment and keep going. The crossing happened because the spacecraft was moving outward and the boundary was in the way. Now, project that forward. 40,000 years from now, Voyager 2 passes near Ross 248. 296,000 years from now, it passes near Sirius. These have sometimes been called destinations in popular accounts of the Voyager mission. They are not. This spacecraft will not slow down. It will not enter orbit. It will not study these stars or interact with them in any way. It will pass through their general neighborhoods at distances measured in light years and continue onward without any change in its condition or its trajectory. The stars will not notice it. It will not notice them. And beyond those passages, there are no more named points on the map. The trajectory extends into millions and billions and trillions of years, and across that entire span, there is no place the spacecraft is going. There is no arrival. There is no endpoint. There is only continuation. Movement without purpose, persistence without destination, existence without connection to anything that gave it meaning. That is what makes Voyager 2's future so deeply unsettling. It is not the distance. Humans have been telling stories about distant places for as long as there have been humans. Distance can be romanticized. It can be framed as adventure, as exploration, as the noble expansion of the known into the unknown. But Voyager 2's future is not a story about distance. It is a story about time. And time, at the scales involved here, does something that distance cannot. It erases the context. When Voyager 2 was launched, it carried context with it. It was a product of human engineering, human curiosity, human ambition. It belonged to a civilization. It had a name, a mission number, a team of people who monitored its health and celebrated its discoveries. It existed in a web of meaning that stretched from the clean rooms of the Jet Propulsion Laboratory to the living rooms of people who watched the Neptune encounter on television. Every signal it sent back was received by someone. Every image it captured was seen by someone. Every measurement it recorded was analyzed by someone. The spacecraft existed because humans existed, and its existence mattered because humans said it did. When the signal stops, that web begins to unravel. Not all at once. The data will remain in archives. The images will persist in databases. Scientists will continue to study the Voyager results for decades, perhaps centuries. The mission will be remembered. But the spacecraft itself, the physical object moving through space, will no longer be connected to any of that. It will no longer be sending data. It will no longer be receiving commands. It will no longer be participating in the relationship that made it a spacecraft rather than an object. And as the centuries pass, and the millennia, and the millions of years, the context erodes further. Not just the connection to the mission team, but the connection to the species. Human civilization, whatever form it takes in the far future, will eventually end. This is not pessimism. It is statistics. No species in the fossil record has persisted for more than a few million years in recognizable form. The average mammalian species lasts roughly 1 million years before evolving into something else or going extinct. Homo sapiens has existed for roughly 300,000 years. Even if humanity survives far longer than the average, even if it colonizes other worlds and endures for tens of millions of years, it will eventually change beyond recognition or disappear. The civilization that built Voyager 2 will become as remote and as incomprehensible as the Cambrian organisms are to us, and then it will become more remote than that, and then it will be gone entirely. Voyager 2 will still be moving. The Golden Record was designed with this possibility in mind, at least partially. Carl Sagan, Ann Druyan, and the team that assembled the record understood that the spacecraft might outlast its creators. The record was intended not just as a message to extraterrestrial intelligence, but as a time capsule, a physical artifact that would carry evidence of human existence into a future where humans might no longer exist. The cover carries instructions for playing the record, encoded in a symbolic language based on the hyperfine transition of hydrogen, a universal physical constant that any technologically capable species should be able to recognize. The record itself is dense with content, packed with more of Earth than any single object has ever been asked to carry, pressed into gold and bolted to the side of a spacecraft destined to outlast the sun. The full contents of the Golden Record deserve a moment of attention, because the weight of what Voyager 2 carries into the dark is not an abstraction. It is specific. It was chosen by specific people making specific decisions about what mattered enough to represent an entire world. The record contains 115 images encoded as analog signals. Among them are photographs of the Earth from space, showing the blue and white sphere that every Voyager engineer saw from the ground each morning. There are photographs of human beings. A woman nursing an infant. A man eating a meal. Children studying in a classroom. Sprinters captured mid-stride. An instant of human motion preserved for longer than the stars will burn. There are images of insects, flowers, fish, trees, elephants, and dolphins. There is a diagram of the structure of DNA. There is a photograph of a sunset. The greetings are spoken in 55 languages, from ancient Sumerian, one of the oldest known human languages, to modern Chinese dialects, each one a voice from a world that no longer exists in the form it took when the recording was made. Some of the greetings are formal, some are simple. The greeting in English, spoken by a child, says, "Hello from the children of planet Earth." The greeting in Amoy, a Minnan dialect, translates roughly to, "Friends of space, how are you all? Have you eaten yet? Come visit us if you have time." There is a warmth in these recordings that is almost painful to consider, given the context. They were spoken into a microphone, pressed into metal, and launched into a vacuum where no ear will ever hear them unless the universe provides an audience that, so far, it has shown no sign of providing. The sounds of Earth include the crash of surf, the rumble of thunder, the calls of birds and whales, the bark of a dog, and the cry of a human infant. There is the sound of footsteps, of heartbeats, of laughter. There is the sound of a kiss. Each of these was selected because it represented something fundamental about the experience of being alive on this particular planet, at this particular moment in cosmic history. The wind, the rain, the first cry of a newborn, the percussion of a human heart at rest. The music spans cultures and centuries. Bach's Brandenburg Concerto No. 2, performed with mathematical precision and emotional depth. Beethoven's Cavatina from his String Quartet No. 13, a piece the composer wrote during a period of profound personal suffering. Music that sounds like grief made beautiful. Chuck Berry performing a song about a boy from Louisiana who played guitar so well that people came from miles around to hear him. Blind Willie Johnson's slide guitar piece, recorded in a studio session in Dallas in 1927 by a blind musician who would die homeless less than 20 years later. A melody so haunting that the Golden Record team chose it to represent the depth of human solitude. A Navajo night chant, panpipes and drums from Peru, percussion from Senegal, a raga from India. Each track chosen not just for its beauty, but for its ability to carry information about the species that made it. The way we organize sound, the way we feel rhythm, the way we convert suffering and joy into patterns of vibration in the air. All of this is on the disc, bolted to the side of a spacecraft that is right now hurtling through interstellar space, and all of it will remain there for billions of years as the spacecraft drifts through a universe that is slowly going silent. There is a recording of brainwaves on the record, Andruyan's brainwaves, recorded over the course of an hour as she meditated on human history, civilization, and what it means to be alive. The data was compressed and encoded onto the disc as audio, an hour of human consciousness rendered as sound, embedded in gold, bolted to the side of a spacecraft, and launched into interstellar space. If the record is ever played by someone or something capable of interpreting it, they will hear the electrical patterns of a human brain thinking about the species that sent this object into the dark. The intention behind the record is extraordinary. The ambition is almost unbearable. To imagine that something you make with your hands could carry your voice, your music, your thoughts, your species across timescales that dwarf the age of the Earth itself. To design an artifact that speaks not to the next generation, but to the next era of cosmic history. No human object has ever been built with a longer time horizon than the Golden Record, and no human object will ever be more alone, because here is what the designers knew, but could not solve. A message requires a recipient, a greeting requires someone to greet, a time capsule requires someone to open it, and the universe that Voyager 2 is heading into may not provide any of those things. The search for extraterrestrial intelligence has been running for more than 60 years. It has found nothing confirmed. This does not prove that intelligence is absent from the galaxy, but it establishes that intelligence, if it exists, is not abundant and not obvious. Whatever the reason, the observable fact is that no one has answered. Voyager 2 carries its record into this silence. The probability that the spacecraft will be physically intercepted by another intelligence is not zero, but it is so small that no serious scientific estimate has ever placed it above the level of a thought experiment. The spacecraft is tiny. The galaxy is vast. Voyager 2 is not broadcasting its position. It is not emitting any signal. After the transmitter dies, it becomes a dark, cold, inert object moving through a dark, cold, inert medium. Finding it would require either extraordinary luck or a search effort so comprehensive that the civilization conducting it would presumably have better things to study than a tiny artifact from a species that vanished billions of years ago. The most likely future for the Golden Record is that it is never found, never played, never decoded. The images of Earth are never seen. The greetings in 55 languages are never heard. Blind Willie Johnson's guitar is never listened to. Andrewian's brainwaves are never interpreted. The message is sent, and it travels, and it endures, and no one receives it. Not because the message failed, but because the universe is too large, too empty, and too dark for the message to reach anyone. This is not a failure of the mission. The golden record was always a gesture, not a guarantee. Sagan himself described the act of sending it as more about the senders than the receivers. The record says something about what humanity valued, what it hoped for, and how it wanted to be remembered. The fact that it may never be found does not diminish that, but it does change what the record becomes over time. It transforms from a message into a monument, and then, as the eons accumulate and the context dissolves, it transforms from a monument into an artifact. And then, as the stars die and the galaxies disperse and the universe cools toward its final equilibrium, it transforms from an artifact into something that does not have a human word. An object that was once meaningful, existing in a cosmos where meaning may no longer be possible. This is the deepest layer of the story. Not the engineering, not the trajectory, not the stellar encounters or the galactic orbits or the timescales measured in trillions. The deepest layer is the gap between what Voyager 2 was meant to do and what it will actually do. It was meant to explore. It explored. It was meant to communicate. It communicated. It was meant to carry a message. It carries one. But after all of those purposes expire, after the exploration is complete and the communication ends and the message goes undelivered, the spacecraft continues. It does not stop because its purposes have been fulfilled. It does not stop because its purposes have failed. It does not stop at all. And the continuation, the sheer, relentless, pointless persistence of a dead machine through a dying universe is what makes Voyager 2's story unlike any other in the history of human endeavor. Every monument humanity has ever built was designed to endure. The pyramids, the cathedrals, the carved faces on mountainsides, all of them are acts of defiance against time, attempts to project human presence into a future that the builders will not live to see. But every one of those monuments sits on the surface of a planet with an expiration date written in stellar physics. When the sun swells and dies, it will take every trace of human construction with it. Not some of it, all of it. Every stone, every foundation, every archive, every fossil. The surface will be wiped clean as though nothing had ever lived there. Voyager 2 left the planet. It left the sun's magnetic reach, and it is on a trajectory that will eventually carry it beyond the sun's gravitational influence entirely, tens of thousands of years from now. It exists in a medium where the forces that destroy terrestrial monuments, weather, erosion, tectonics, stellar death, either do not apply or operate so slowly that the spacecraft will persist for billions of years beyond anything left behind on the ground. Voyager 2 is not humanity's greatest scientific achievement. It is not humanity's most important discovery, but it may be one of humanity's most enduring physical objects. Among the last things made by human hands that still exist in the universe, long after the hands and the species and the planet and the star are gone, there is a specific moment in the future that is worth holding in your mind. It is not a dramatic moment. It is not a collision or an explosion or a discovery. It is the moment, billions of years from now, when the last human record on Earth is destroyed. The last archive, the last hard drive, the last carved stone, the last fossilized bone. Whatever the final physical trace of humanity on Earth is, there will come a moment when it is erased by heat, by radiation, by the geological recycling of a dying planet. After that moment, the only evidence that humanity ever existed will be the objects it sent into space. The Voyager spacecraft, the Pioneer plaques, the handful of other artifacts drifting outward. And of those, the ones that carry the most information, the most deliberate attempt to say we were here, and this is what we were, are the golden records on Voyager 1 and Voyager 2. After Earth is gone, those records become the primary archive of human civilization. Not a backup, not a copy, the original, the only one, carried on objects that no one can reach, no one can maintain, and no one can read, drifting through a galaxy that is slowly going dark. This is why the phrase final destination requires careful handling when applied to Voyager 2. 250 trillion years from now is not a place Voyager 2 arrives at. It is not a star. It is not a planet. It is not a coordinate on any map. It is a point in time, inconceivably distant when the spacecraft still exists. But everything that made it matter has been gone for so long that the gap cannot be measured in any unit that carries human meaning. The final destination of Voyager 2 is not a location in space. It is a condition. The condition of being the last remnant of something that once lived, moving through a cosmos that has forgotten what living was. And that condition is not terrifying because of what happens to the spacecraft. Nothing happens to the spacecraft. That is the point. It does not crash. It does not burn. It does not collide with anything or fall into anything or get captured by anything. It just keeps going. Through the death of the sun, through the merger of galaxies, through the extinction of stars, through the cooling of the universe towards a temperature so close to absolute zero that the distinction between matter and emptiness begins to blur. The spacecraft persists because nothing stops it, and nothing stops it because the universe is too empty and too vast and too indifferent to notice it. The horror, if that is the right word, is not in any single event. It is in the accumulation of time without event. It is in the silence that begins when the transmitter dies and never ends. It is in the realization that the loneliest moment in Voyager 2's existence is not the moment it loses contact with Earth. It is every moment after that, compounding, stretching, extending across a future so deep that the word future starts to lose its shape. There is no rescue. There is no rediscovery. There is no ending in the narrative sense. There is only a machine built by a species that existed for an eye blink of cosmic time, continuing to move through the dark long after the eye blink is over. And yet, there is something in that persistence that resists the darkness. Not in a sentimental way. Not in the way that stories about Voyager often end, with warm words about the human spirit and the power of exploration. Those words are true, but they're not enough for what this story asks you to hold. What resists the darkness is simpler and stranger than that. It is the fact that Voyager 2 exists at all. That a species living on a thin shell of rock around an ordinary star in an unremarkable corner of an average galaxy managed to build something, anything, that will outlast the stars. Not because it was designed to, not because anyone planned for this outcome, but because the act of reaching outward, of throwing a small machine into the void with no expectation of return, happened to produce an object whose trajectory extends beyond the lifespan of every natural structure in the observable universe. That is not a consolation. It is not a moral. It is a fact. And it is the kind of fact that does not resolve into comfort or despair, but sits between them, asking you to hold both at once. The spacecraft is alone. It will always be alone. It carries the voices of a world that will not exist for much longer on any cosmic clock. And it will carry those voices through a silence so complete that even the concept of sound will have no physical referent in the space around it. But it will carry them. Not to anyone. Not for anyone. Just onward. Through the dark. Through the cold. Through the long, empty aftermath of everything. Somewhere in interstellar space right now, carried forward by a push it received from Jupiter, Saturn, Uranus, and Neptune, before most people alive today were born. A small machine, barely 3/4 of a metric ton, is crossing a stretch of vacuum so empty that a volume the size of a house would contain fewer atoms than a single breath of air contains molecules. It is transmitting a signal so faint that only a single 70-meter antenna dish in a nature reserve outside Canberra, Australia, can still detect it. Within a few years, that signal will stop, and the machine will continue, carrying a golden disc etched with the sound of a humanelli heartbeat, a human song, a human greeting in a language no one will speak 1,000 years from now. It will carry these things for a very long time, longer than the sun will burn, longer than the stars will shine, longer than the word long has any right to reach, and it will never arrive. That is Voyager 2's final destination. Not a place, not a star, not a moment of contact or discovery, just an unbroken line drawn through the dark by a species that wanted, more than anything, to say it was here. The line does not end. There is no one left to draw it, but it does not end.